Today we're just continuing our discussion of dissociation constants. So it's going to kind of be a continuation from last night. So letter C is simply going to be bases, and letter B should have been acids. And this is going to really be just information that you could probably get if you weren't taking notes. But the first thing is we can have strong bases. And strong bases are things that dissociate 100%. So identical to strong acids in the fact that they completely break up. Or we're going to say they break up 99.999%. Okay? So if we have, let's kind of make up a fake equation, some base, BOH, and we put it into water, it's going to break up into B pluses and into OH minuses. Alright? And if we set up an ice table for something like this, we would simply ICE. Alright, if we started with a 0.1 molar solution, 0.1, I got 0 initially, this is going to change negative x, this is going to change positive x, positive x. At the end we're going to have 0.1 minus x, and it's essentially going to be 0, because x is basically pretty close to 0.1, and then we're going to end with 0.1, and we're going to end with 0.1. Okay, so our dissociation constant for a base is simply going to be Kb. Alright, and what does Kb equal? Well, Kb equals our, that's what that was. It is our, whatever our cation happens to be. So possibly sodium ion, calcium ion, lithium ion, any of those. Concentration of it times the concentration of hydroxide, all over our base when it was together. So BOH. Alright, and given this problem, we essentially get something like this, where we have 0.1 times 0.1 times a really small number, so approximately 0. But again, if we're dividing anything by a really, really small number, we get a very large number. Alright, so just like Ka's for strong acids were large numbers, Kb's for strong bases are going to be large numbers as well. Alright, so the other types of bases we can have are weak bases. And weak dissociate less, let's say, dissociate less than 100%. Alright, so again, if we had just a fake base, BOH, turns into B ion and hydroxide ion, and let's say it's a 0.1 molar solution again, and we're going to have our ice table, ICE, we don't have anything to start with, don't have anything to start with. This is going to change minus x, this is going to change positively x, and at equilibrium, we're going to have 0.1 minus x, and we're going to have x, and we're going to have x. So in this case, our Kb is going to equal x times x all over 0.1 minus x. Okay? And these are going to typically be small values. Again, we're going to assume that x is really small, so really this just turns into 0.1. And then you can find constants, Kb constants, on page 664 in your book. Alright, and you're going to be flipping to that page as well as, I think it was from yesterday's notes, 657 possibly. If you bookmark those pages, it would be pretty smart because you're going to be using those often. Okay. And the same process, you're going to solve for concentrations at the end. Okay, so we're going to skip that part of our notes today. Alright, the very last thing is we want to look at the relationship between Ka and Kb. Alright, so relationship of Ka to Kb, and we might also say for acids, slash conjugate base, or base and conjugate acid. Okay? So relationship of Ka to Kb, and for an acid conjugate base or base conjugate acid. And it all, you'll see here in a second, it's all kind of tied together. So if we take nitrous acid, okay, instead of nitric acid, so nitrous comes from the nitrate ion, whereas nitric acid comes from the nitrate ion. Okay, and this is considered a weak base. If we put it in water, we're just going to put water here this time, it's going to turn into H3O plus and NO2 minus. Alright? So we kind of have acid base, conjugate acid base, conjugate acid, conjugate base. Alright? And then if we start with, kind of just on the other side, if we start with the conjugate base this time and add it to water, we are going to get HNO2 and hydroxide. Okay, so notice that one of these we're getting the hydronium ion if we start with the acid. If we start with the acid's conjugate base, we get the hydroxide ion. So a couple things from this. This is going to have a Ka value, alright? And Ka, water is a pure liquid. It's really Ka over here is equal to the concentration of hydronium times the concentration of nitrate all over our acid, HNO2. If we look over here, because we're making a base, it's going to have a Kb value. Right, and our Kb value is going to be HNO2 times hydroxide. And again, water is a pure substance all over nitrate ion. Okay, so good. Now what I want you to imagine is if we add this equation and this equation together. Alright? So let's change color. And we're going to add these two equations together. I'm going to just put it down here. So if we have HNO2 plus water yields hydronium plus nitrate, and then we also have nitrite plus water yields nitrous acid and hydroxide. So if we add these equations together, kind of like we're doing like a Hess's law problem or something like that, we would see, we kind of cancel things that are the same on both sides. We have nitrite on both sides, and we have the acid on both sides. So as we add these up, we get two waters that yield hydronium ion plus hydroxide ion. Alright? Okay, that is kind of clear. So the other thing is, if we look at, alright, and what is this? Is how we get our Kw for water. And what is the Kw for water? It is hydronium concentration times hydroxide concentration. And what's true about that? It always equals 1.0 times 10 to the negative 7th. Okay? So if we have these equations and kind of think back to equilibrium constants, if we want to multiply these equations together, or really add them up, we're going to end up multiplying. So if we multiply Ka times Kb, we're basically just going to multiply our equilibrium expressions as well. So our equilibrium expression for Ka was hydronium times nitrite all over nitric acid. And then we're going to multiply that by our Kb expression, which was nitric, or nitrous acid, I keep on saying nitric, times hydroxide all over nitric ion. Okay? So, or nitrite ion. So again, if we kind of look at this, we're going to see that several things cancel as we multiply through. Our nitric acids, nitrous acids are gone, and our nitrite ions are gone. So really, if we multiply Ka times Kb, we get hydronium ion times hydroxide ion. Alright? And we know that this, again, is always 1.0 times 10 to the negative 7th. So we also know that Ka times Kb equals 1 times 10 to the negative 7th. So if we look up, let's say if we look up nitrous acid for real, its Ka value is 4.5 times 10 to the negative 4th. So if we needed to know its Kb value, okay, so we just said Ka times Kb, and we know that Ka times Kb always equals 1 times 10 to the negative 7th. I'm sorry, it does not equal that, and this does not equal this up here. Kw equals 1 times 10 to the negative 14th, which means that both hydronium and hydroxide are 1 times 10 to the negative 7th. And again, hydronium times hydroxide is not 1 times 10 to the negative 7th, it is 1 times 10 to the negative 14th. Likewise, this is always going to be equal to 1 times 10 to the negative 14th. Alright, so Kb, we're just going to divide both sides by 4.5 times 10 to the negative 4th, and we can find fairly easily that Kb equals 2.2 times 10 to the negative 11th. Alright, and again, these are concentrations, so we might give it a value of molarity, or molar. But again, if you look on those pages, I think 657 and 664, 657 has Ka values, but it also has the Kb value for that Ka's conjugate base. Likewise, on page 664, it has Kb values, but it also has the Ka for that weak acid's conjugate acid, or that weak base's conjugate acid. So again, a great thing to know, Ka times Kb always equals 1 times 10 to the negative 14th. And again, make sure that that's in your notes as 1 times 10 to the negative 14th, not 1 times 10 to the negative 7th. Okay?